Good afternoon, everyone. I appreciate you joining this call. As Laura said, I am going to be talking about how I am using Paradise to find hydrocarbons using SOM classification. I'm not going to read this, but since this is being recorded and people can refer back to this later, this is kind of my take on what Paradise does and what does it do. And basically, the SOM classification that I've been using is cluster analysis or pattern recognition using multiple seismic attributes at one time. The important part to remember here is that instead of using or looking at a wavelet as we traditionally have in the seismic domain, we have gone down to sample statistic resolution. And this is important because this allows us to see thin beds, thin porosity streaks and carbonates, so on and so forth. What I do want to point out is this is not a one and done operation. This is experimental, and you're calibrating to your well information, which is critical. So if you use too few neural classes or you're looking for too few patterns, then you have a tendency to aggregate the natural patterns that are there in the subsurface. And if you use too many neural classes, you run the risk of breaking up the patterns into pieces too small to accurately interpret. That's one of the main elements here in using Paradise. When I talk about sample resolution, a traditional wavelet, depending upon the frequency of the data, could be 30 or 40 milliseconds. Well, if you are mapping a peak or a trough or a zero crossing, you're parsing that data 4 times. However, if you are working with 2 millisecond sample intervals, you're looking at that data 20 times. So you're getting 5 times as much information out of the data as you normally would if just mapping a peak or trough or a zero crossing. And that's really important when you're looking at thin beds. And why we use multiple attributes at one time is that on every trace at every sample, we're getting a little bit information. And that information sometimes is related to other attributes and sometimes it's not. So that's what's really important. And to that is, if you look at each attribute individually, they all have different wavelets. So every sample on every amplitude or every attribute is going to give you a slightly different number. And that's important in the attribute world when we're looking at the natural clusters of information as they form. Why this is important and what we're seeing here is what you end up getting. I call these chiclets, but they're really pixels. And they're determined by the bin size of your data by the sample height. And in regular seismic wavelet work, we talk about tuning frequency. And so yada yada, you might not be able to see a bed of sand that's 20 feet thick at 10,000 feet. But here the tuning thickness is dependent upon the interval velocity of the rock at that sample. So if you're working in carbonates, obviously you're not going to see something as thin as you would if working in clastics because the velocity is much greater. Now, a lot of people ask me how I determine my recipes, and I like to cook, so I call these combinations of attributes recipes. And the first process that we normally go through is a process called principal component analysis, where we can take a big bunch of attributes and reduce it down to those attributes or that much information which are really key and meaningful to the zone of interest in which we're interpreting. And just quickly looking at it, the first principal component is going to be the longest axis. Now this is a case where I have only 2 attributes. So the longest axis is the first principal component, and the second principal component is orthogonal to that. Well, that's fine if you're looking at 2 or 3 dimensions, but what happens if you're using 8 or 9 different attributes? Our brains can't comprehend 8 or 9 different directions, but the computer can. And so the ultimate result of that is that we can go through, and all these lines up here in the left, all these represent the principal components analysis done on each individual inline in a 3D. So I'm looking at the highest eigenvalue on the first eigenvector, and there are 4 attributes which make up for more than 93% of the information available in all 12 attributes that I used. So obviously these 4 carry the biggest amount of weight when I'm going to create a recipe to look for something. And then if I go to the second highest eigenvalue, these 3 attributes, dominant frequency, and instantaneous Q, end up being 81% of the remaining information that the first 4 didn't catch. So right here, I've taken 12 different attributes and down to 7 key attributes that I'm going to use in my first recipe. Now, my years of using Paradise all over the world at this point have told me that this is a great place to start. But if you're not calibrating to your wells, or if you're not seeing the information that you think you ought to be seeing in the data, then that's where I start substituting attributes and playing with the recipe a little bit. Just kind of like someone would add more salt or take away a little bit more pepper. That's what you do in a recipe. So without further ado, I'll get into some of the things that I've done over the past few years to help find out hydrocarbons for myself and my clients. First is a thin bed example of a discovery I had in Brazoria County, Texas. And the client approached me with an idea that he'd been given by an engineer, saying that there was a well right in here, if you can see my cursor, if you can see my pointer, that had produced about 450,000 barrels of oil. And there were several wells down here that had produced 20 or 30,000 barrels. They weren't great producers, but they were from the same sand. And so his idea was that that the sand covered this whole fault block right here. And so my client said, well, you know, what do I do? And I said, well, A, you have to get a 3D if you're going to sell a deal. And I have to map it, and we have to tie to it and see what's really going on here. So what's critical about using sample statistics is how good your synthetic ties are to the data. You can get sloppy in the wavelet world, but you can't afford to get sloppy in the sample world. And this was really good data. I had a very easy tie, and it looked like that the perforations, 7 feet of perforations right here, ended up tying to a very thin, wispy little amplitude that you couldn't even map. So what I had to do is I had to map the trough above it, and then later on I flattened that trough and did a series of flattened time slices to see the aerial extent of this amplitude. Now, I ran my first recipe with this, and this is a strike line kind of down that fault block, so you can kind of see where this wispy little amplitude kind of comes and goes throughout. And here's the good well, and here are the 3 poor wells down here at this end on the west side. Now, in Paradise, I use things like sweetness, relative acoustic impedance, instantaneous phase, instantaneous frequency, because I knew I was dealing with thin beds, and several other attributes to help get an idea of what was going on here. And as you can see from this enlargement, here's the good well right here, and it looks like it's tying to some kind of maybe an offshore bar. And the sand, it looks like, stops very shortly after the well. So you can see a very faint little peak event coming right here, and then by the time you get to the end of the sand, that peak event is gone. And if you look down the line, again, the kind of the blue and the green colors right here represent what I'm calling an offshore. You can see that they get pretty sparse over here where the poor wells are on the left side, and here's where the perforations are in the good well. Again, this black line represents a flattened time slice of the trough that I used above that wispy little amplitude. Now, here's a flattened time slice showing the good well and the well that I recommended to my client and the 3 poor wells. And when you start looking at the 3 poor wells, the engineer who brought him the idea said that they were mechanical failures. But I think what's really happening here is they didn't produce very much because they were on very thin pieces of sand, or very small pieces of sand, 20 or 30 acres. And my interpretation of this is that this orange area could be an incised or a tidal channel cut, which could be compartmentalizing the production from the really good well, and hopefully that my client well might take some of the reserves out of the good wells area. When you look at a up, this red box right here represents the 80-acre production unit. So what we did is we came a legal location in the state of Texas, which is 467 feet outside the production unit, and to drill the well. And indeed, we found 6 feet of pay right here in the Alabel sand, which is a middle Frio sand. And we had 4 feet of pay in a grub, another little offshore bar in the grub sand above it. So here's the bar development right here. And that well came on for 250 barrels of oil a day and 1.1 million cubic feet of gas. Now, in Paradise, what you can do is you can turn off all of the patterns, all of the neurons, except the 4 or 5 that represent the sand body in this case. So that instead of using a flattened time slice, I can show the whole areal extent of the sand deposition as it occurs in that fault block to be a lot more accurate. And this is my recipe again. Imaginary part, instantaneous frequency, use the amplitude volume, relative acoustic impedance, thin beta indicator, and trace envelope. Now these attributes were done before we started getting the ASPE attributes in Paradise. So this was done using rock solid right here. And to bring you up to date, since that well was drilled, the original operator didn't like us drilling so close to their production unit. So they stepped out on the other side of that little insides cut, although they didn't realize it was there, and built a new well in 2017. And that well so far has a cum of 615 million cubic feet of gas and 56,000 barrels of oil. Here's the well my client drilled, and since then, they've come down here and drilled another well. And this well actually was targeting the grub sand, that 4-foot thick sand that we could see. And that well has already made a little bit over a half a BCF and 53,000 barrels of oil. So of the 4 wells in here, not including the poor wells down here, this little 7-foot thick bar sand has now made 1.2 million barrels of oil and 10 BCF of gas. So if we could find 100 more of these in Brazoria County, I think that we could have a pretty good run on oil and gas. This next example is some work I've been doing with some clients since 2013. And basically, it's a lap out play or a pinch out against structure in southern Oklahoma of a Pennsylvania aged sand. And the critical part to this is you can map a reflector up to the point where it pinches out, but you can't see where the sand itself pinches out without using this type of technology. Now, in this case, we have gone down dip and even have one more well down dip from this and have yet to find a water leg in this. But I have gone too far up dip and absolutely missed the sand altogether. But this green neuron right here is what we're chasing. And the idea is that we're looking for these lower Pennsylvania sands as they come up on the shelf and pinch out. Now, in this case, I've got one sand down here that never made it up on the shelf and stayed wet. The sand we're chasing comes up on the shelf, pinches out against structure or up against shelf or dip, and then there's an upper sand that goes on off our 3D. So all I do here is I map the event, then I flatten on it, and not quite like shooting fish in a barrel, but we just march our way down the pinch out edge, staying back a little bit so that we don't not too thin a sand, and just drill our wells. Now I have a field near this example that I'm showing in which we have been successful 17 out of 18 wells. So this is a pretty good technique to use. Now, this is a discovery I had, and I had a 3D where I was looking at a down-thrown lower Wilcox field. This field had produced 80 BCF and 800,000 barrels of oil from sands in the lower Wilcox from 13 to 15,000 feet deep. And there was a bunch of middle Wilcox pay in this too. And traditionally, I'm on Kingdom, so I've gone through and I've used things like sweetness and average energy to look at, in the classic domain, to look at where I might have hydrocarbons and good porous sands. So I thought this was pretty interesting that I could define most of the wells in the field by using those two attributes. Here's an example of the sands. They're nice, thick, beautiful Wilcox sands. You just perf them and frack them, and they produce like gangbusters. The average well makes about 10 BCF and about 80,000 barrels of oil. Plus, there's a bunch of middle Wilcox pay behind pipe in this area. Now, I use a technology, or I use part of Paradise that people don't get into very often, but we call it a low probability volume. And it goes anti-goggling to the way one's mind thinks, but the low probability means that really the probability of any of these outside data points being at the center of the cluster is very low because they're outside data points. And what I found in looking at this low probability information is that if I'm using hydrocarbon indicating attributes, or I'm using AVO volumes, because you can use AVO volumes or offset stacks or anything you want as attributes in your recipe, as I'm using these, I find that a lot of my AVOs, or my hydrocarbon indicators, are actually found in these low probability data points. And you actually have a slider that you can go back and forth and use. So in this case, I want to see my lowest 10% probability. So the color bar to that is a color bar where you have 10%, in my way, I have 10% of the lowest probability from 0 to 100% as white. And then I just kind of have a whole bunch of other colors in the background. Here I'm showing the low probability anomaly in this field. And the low probability is actually tied to those wells which are 10 BCF or greater. The wells which were less than 10 BCF don't show up with a very good low probability anomaly. And the field actually has a high, and then it goes into a low, and then it comes back to a high again, which is why you're seeing these two separate units. Now over here, I have the low probability display on top of the classification, or the pattern recognition. And this is my recipe: attenuation, average energy, the amplitude volume, relative acoustic impedance, envelope bands on envelope breaks, envelope bands on phase breaks are very similar to what Kingdom has as average energy and paraphase. And then of course I use sweetness. Now, I noticed when I was looking around that I had a response from the upthrown upper Wilcox fault block, which had no wells in it, similar to what I had in the downthrown field. So I ran the same recipe over the upper Wilcox, and lo and behold, I had a really nice low probability attribute, low probability response using the same recipe I did on the lower field. So I got my partners involved, and we went to NAPE, and this is the display we showed at NAPE. Here's the downthrown field, 80 BCF and 80,000 barrels of oil. And here's my upthrown prospect area. Here's the low probability anomaly for the downthrown field, and here's the low probability anomaly for the upthrown block. Now, even though this is lower Wilcox and this is upper Wilcox, Paradise is still seeing, using the same recipe with those hydrocarbon indicators, still seeing this is very anomalous. So we sold the deal in 4 showings. And when I looked at, I did a run that covered both the upthrown and downthrown zone so that I could look at the neurons that were in common. Again, here's the group of 10 BCF or better wells here and here. And then here's my prospect area. And I'm going, well, that looks pretty good. So we drilled the well in 2016. And we had to deviate in because the lady wouldn't let us drill on her property. But we drilled this first anomaly right here. And we had excellent shows. This is the Schlumberger log analysis, and this is the mud log. Now this piece of mud log right here with all these shows is expanded to show the actual Schlumberger analysis on the well. And I want to point out that we still haven't drilled this. With the price decline and the problems, the operator is not intending to drill another well in here. This first zone that we perforated, however, is still producing for the last 4 years, and it's made a little bit over 2 BCF of gas and 30,000 barrels of oil. And we have all this stuff to complete in behind Pike. And here's the first zone that we perforated. We went to sales on a 11/64 choke, making 3.2 million a day and 150 barrels of condensate a day at 6,700 pounds of flowing tubing pressure. And I have a little movie here, but I didn't get it started, so it was just the flare and a bunch of noise, so you probably can live without that. Now this next area, I do a lot of work in Wharton County, so I kind of have my recipe down for Wharton County and other areas in the Gulf Coast. And I was looking at some old production down here in a field, and I have my 2 key neurons turned on, and noticed I had a really nice area upthrown to this old production. Now this is a new well, and this is old production here, so the responsiveness is coming from rock quality, not necessarily hydrocarbons in here. I don't have angle stacks or gathers in here, so I can't prove there's an AVO response, but I do know from experience in here, especially since this is a new well drilled after the 3D was shot, that this is probably a pretty good area to look for hydrocarbons. And again, I'm looking at low probability, just like I did with my Wilcox discovery. So I've got low probability left over from this field. I have low probability. Now this is the new well right here. Low probability from this depleted area, low probability left over from this area, and then I have my prospect area that I'm interested in. And this is the prospective area. Now this well right here is structurally low, but did have a show in the upper Wilcox, which is important. And this is the down-thrown field that you're seeing right here, okay? And it's not showing a full green response. I'm looking at the stack. I like to see the white over the yellow, over the greens and blues. Here it's kind of broken up, but this field was found in 1964 and is depleted. So you don't expect to see a concentration of hydrocarbon indicators, you know, in depletion. Here you've got a really good response. Now what I've done is I've gone in and here's another thing that we can do is we know the bin spacing of the 3D. We know the sample interval. So from that we have a volume, and we can create geobodies that represent the volumes. And the exercise here is I looked at the geobody that was related to the down-thrown production, and using some estimates for the area, I came up with an estimate of reserves of 4.659 BCF. Well, that field had produced gas and oil, so I multiplied the oil by 7 to get a gas equivalent. And if you look at the total production of the field, the actual production in a gas equivalent is 4.809. That's only a 4% error from what I was estimating out of the geobody that was calculated in Paradise. Now, using that same information, I applied it towards the geobody up here where my prospect area is. And obviously, it's going to take more than one well to get all this. But using the same numbers, I came up with an estimate of reserves of 15.2 BCF of gas equivalent. Knowing that the upper Wilcox here is probably about 10 barrels per million. It's not real high in condensate in this area. But that's enough at 8,900 feet to get someone to go drill this. The unfortunate thing is, once I did all this work and checked on it, I found out that it had all been leased. So I'm still patiently tapping my toe and waiting for the leases to expire. And just to show you that I think this would be a good prospect, regardless of the fact that I have Paradise to help kind of prove it up, is that I have anomalies that indicate there's hydrocarbons here. I have a sweetness anomaly in the yellow circle. I have an average energy anomaly in the yellow circle, and here again is the well that had the show, but is slightly structurally down dip. I have an energy absorption volume right here that shows an anomaly, and then using my relative acoustic impedance, which I use a lot to help me find porosity, I have a nice relative acoustic impedance anomaly here as well. So even though I use Paradise to help reduce risk and help me estimate my reserve potential, it gave me indications of being a decent prospect or a good lead just because of the other attributes that I used. Pause for a sip. Sorry about that. Okay, so there's times when I find hydrocarbons, and there's times when I have clients that hire me to see if something is worth drilling or not. So while it's not finding hydrocarbons, it's avoiding a dry hole, or even more disastrous many times, an uneconomic well. This first case is South Louisiana, very deep. As you can see, the depths here are 21,000 feet. And so my client had put together a prospect, had basically almost sold the deal as a lookalike to this discovery well right here back before 2014. Well, obviously, when the prices crashed in 2014, a lot of people backed out of the deal, and they lost the leases, and they went on their way doing other things. So they approached me last year to see about running Paradise on this, to see if it was economic to put together and what I thought. So they have a structural closure, just like this well did, and they have a nice little fault block between them. You can make the jump over this area right here. There is another producer in the area, but it produced from a lower, different sand, and then everything else is pretty much a dry hole in here. So this is the amplitude data, and again at 21,000 feet, it's not the world's best data. And the mapping that they gave me, because I didn't do any additional mapping, I just took what they gave me, left a lot to be desired. So, you know, sometimes it drives me crazy when I see people who pick faults and things that go awry. But basically what they're chasing is this 300-foot thick Chris R massive sand. And I've done a blow up here so you can kind of see the log curves a little bit better. But I've got a massive Chris R section, and then I've got some good Chris R sands down here below that they perforated. This well has made about 40 BCF and, gosh, 2 or 3 million barrels since it was drilled. Now, one thing I noticed is that it's got this nice little limestone cap on top of it. And my client's fault block, which is right here, does not appear to have that same limestone cap. Here, this green line represents the top Chris R sand, and the red is the base of the Chris R down here. So pretty massive sand. So that kind of was a red flag to me right there, because you've got to have a seal, especially in these highly pressurized reservoirs. And if you don't have a seal, then any gas you might have had in the Chris R sand could have leaked off, and there is a shallow field over this structure underneath where they were thinking about getting acreage. So I had the far angle stack here, and I ran my recipe using the far angle stack. And what I noticed was that, yes, I'd had some kind of vertical percolation which charged the limestone, and it changed the rock properties of the limestone to this kind of greenish color. And if you'll look closely, this red, or this blue area right here, is sitting down on top of this green here. But as you get away from the reservoir, you kind of go into this brown and white and red patterns. So there's almost evidence of a flat spot right here for the reservoir. And the green in the limestone cap kind of goes away, except for right here. And you can see many of the same stack of neurons or patterns as you do in the discovery proper. But you don't see any of that information over here in my client's area. And looking at that, and just one neuron where that green is in that limestone, here's the discovery well. Here's my client's proposed location. And this basically is the reservoir. It's showing you the reservoir that this discovery well is producing from. This is the well that produced from another sand. And then that other area, let me go back, that other area right here happens to be this little channel right here that's not connected to the field. So there may be a chance in the future where someone could come down dip, believe it or not, and find still a very good reservoir for gas. This is my recipe. Most of this came out of the principal component analysis. And again, I used my far angle stacks to create my attributes so that I could see some kind of AVO effect that was going on in here. Now, another case, and this time it's a carbonate case, where a client hired me, and let me just kind of finish this story. Well, obviously, my client, I advised not to put the acreage together and not spend $30 million to try to get this deal put together and drill a well, because I didn't think it was going to be successful. So that's kind of the end of that story. So I have another client, again, who was looking at a prospect, and this time it's in a Pennsylvania reef in West Texas. So I have a really good field here that's made 1.5 million barrels of oil and a little over half a BCF of gas from a Pennsylvania reef at about 8,500 feet. No pipe in this area. And then he was approached by a guy who had a prospect over here with a show well that had made a little over 2,900 barrels. Now, in looking at the reef mapping, here's the old field. This field was discovered, in the 80s and 90s. And here's the prospect area, and here's the show well. So the gentleman who was selling this prospect said, look, I know it's not 1.5 million barrels, but I think there's at least 300,000 or 400,000 barrels here, and that would be very economic to drill, put the acreage together and drill. So my client said, okay, Deb, I'm going to get you 5 square miles of data. I want you to look at this and tell me what you think. So I mapped a lower surface just so that I could run my analysis between the top of the reef and what I'm calling the base of the reef and kind of pinpoint the zone that I'm looking for. And then I ran my analysis. Now here's the amplitude data. So here's what I'm calling the upper reef. Here's the prospect area. Here's the show well right here. And then here's the 1.5 million barrel field. Now it looks like there's 2 reefs here, but I've just taken my arbitrary in and out of the plane of the reef to catch the better wells. And then here's the surface that I mapped as the lower part, but we'll see in the next slide that it really is not the base reef after all. So again, I use the familiar culprits of instantaneous phase, instantaneous frequency. Relative acoustic impedance really works well in carbonates because it's showing you what's relatively hard or soft, which is a good porosity indicator. I use sweetness. I use normalized amplitude in here, so I have a nice combination of attributes. Now, you can tell when you start looking at this, the true base of reef, because you can see this kind of little light green line that represents the base of the carbonates as they sit on a clastic rock below. But what's most important is this red, orange, yellow area in the central part of the reef that represents the porosity. Now, the reason why it's so many different colors is probably because there are different levels of porosity. You could be 16%, 18%, 20%. You could have different permeabilities in here. But what's important is that the core area away from the rest of the reef, which is kind of blues and greens, is where the perforations are occurring and where the production is coming from. Now, I don't see a real big area over here in the prospect, and I hardly see anything where I have my show well. So in looking at this, I've turned off everything that wasn't pertinent to the porosity or the production in the main field. And so here's what you see. Everything here are the wells that are drilled 7,000 feet or deeper. This well was going for reef, but missed it and ended up producing from the San Andres in the area. So here's the prospect, and here's the show well right on the edge of a little piece right here. But you notice they're not connected. If they were connected, you might have a chance of making 150,000 barrels of oil. But being totally separate, it makes it very questionable whether a well drilled in the prospect would be economic at all. And so what I did is I overlaid that information on top of a base map and I planimetered it. And it turns out that the main field is about 133 acres. The show well is right on top of or close to about 4.2 acres of reef, productive reef, and then the prospect is approximately 7.6 acres. So here I don't think you're going to get 300,000 barrels. So I advise my client not to go spend about $2 million to get the acreage and drill the well. So yes, it didn't find hydrocarbons, but it kept you from drilling a dry hole or an uneconomic well. So what do you do about carbonates? Situation where I had a client that came to me and they had shot a beautiful 3D looking for shallow Austin chalk production. And there were 3 wells up here that were drilled in the 60s that had made about 158,000 barrels between them. One of them had produced 128,000, so I made the bulk of it, at 2,100 feet in the Austin chalk. So they shot and acquired this data at 1 millisecond. So I was able to upsample to 1/2 millisecond. And what we found is that we can take the sample rate of a 3D and we can cut that in half without introducing any additional noise or artifacts that affect the pattern recognition part of it. So when you're dealing in carbonates, because they're so fast, the smaller sample rate you can get to without introducing artifacts, the better for you to be able to find thin streaks of porosity. But my client had shot this beautiful 3D. They had drilled 3 or 4 straight holes and attempted a couple of horizontals without finding any economic oil. Now, their original idea when they brought this project to me was that they thought that this key play for oil was looking along a fracture system. So they were trying to stay in the same fault block or similar fault blocks to the structural position of these wells. The first thing I did was pull a gather at the well. Now I know these wells were drilled in the 60s and they were depleted, but the gather, and we're dealing with the carbonate, so I'm looking at the change in angles of the amplitude. That's a peak amplitude for carbonate rather than a trough amplitude. And notice that there was still a slight AVO effect. Now, Rocky and I have discussed this, and while we don't think it's still indicating a presence of hydrocarbons, although when you deplete, you always leave something behind, but we think this is more of an indication of porosity in the carbonate itself. And this is my recipe. I used the far angle stacks, and again, I'm down to a 1/2 millisecond sample rate here. So this well and this yellow neuron right here ties perfectly to the production in all 3 of the key wells. This arbitrary line happens to go through 2 of the key 3 wells. And you notice that I only have 24 feet of perfs here. So that's only about 4 samples. And this one had 21 feet of perfs, which is only about 3 samples. So 1.5 milliseconds or 2 milliseconds for seeing the porosity in these wells. And what you'll also notice is that where I have reservoir, I have a completely different set of patterns or stack in the neurons than I have everywhere else. And I don't just dote on the one neuron that ties my perforations. I'm looking at the whole assemblage of stacks. So I call this my main neuron, and these are kind of my support neurons. What I've done here is I've shown the main neuron, neuron number 71, and I've shown the support neurons that go with it. And I didn't see, when I first looked at this, I didn't see what I was thinking should be a fracture pattern. Maybe something in here might be related to fracture or faulting. And the wells that are right here are producing from the lower part of the Austin chalk, not the upper like this is. But what I see here is more of a channel type trend, or more of an incursion into the top of the Austin chalk and not fractures. And what I want you to notice is up here when I have all of the data points turned on, this is all of the data points that make up these clusters. Now this next slide is I have only showing the lower 10% here, lower probability again. So here is where lower probability is now saying, okay, all this is depleted, so it's no longer anomalous, but all these areas in red and green for my main neuron and support neurons are showing they don't go away. So that means these hydrocarbons are still intact and still in the rock, whereas this is showing my depleted area. Now I'll go back again and say, here we see all of the data points turned on. And here we see only the 10% most anomalous data points to each cluster turned on. So not only can you use lower probability to help you find hydrocarbons, you can actually use it to help you prove depletion in an area. And to show my client that, you know, sometimes you go into an area with a preconceived notion, like they did, that it's fracture related. And the natural clusters in the data will help prove or disprove some of your preconceived ideas. So I got their mind kind of wrapped around the fact that this was channel oriented, and I ran a Sobel filter similarity volume from Paradise using the ASPE attributes to show them that you actually do have channels. Now, this is the Austin chalk, and this is the little carbonaceous sand that just eroded down into the top of the chalk. And you can certainly see evidence of channels coming through the chalk. I kind of highlighted one here, but you can see these channels coming through. And so it's not inconceivable that these little sands are deposited in some shallow erosional feature in the top of the chalk when it was subaerially exposed, and then later charged with hydrocarbons. Now, I've done some work in unconventional and certainly would show that. But I think what's important with this example is that, and this is work done by Patricia Santagrossi, who's also a consultant with Geophysical Insights in the Eagleford. And the beauty of this is for the last 50 years I've been working in seismic data, I've always wanted to get my information close to, if not at, log scale. And for the first time, we can take the 30 milliseconds that becomes the Eagleford Shale, and this is work that she did for a client to help them find sweet spots and prove or disprove where their production was coming from. And we can go through 30 milliseconds of information, find 6 different facies classes, and relate that directly one-on-one with the log curves. So you can see the ash bed, you can see this gold streak in here, and she's pointing to the various, and what's most important is this kind of darky red zone right here, and that is the high resistivity, higher TOC zone that everyone's trying to find in the Eagleford. So using this kind of technology, this classification, not only can help you in conventional clastic or carbonate work, but it can also help you find the sweet spots and stay and not porpoise in and out of zone, stay in zone to help you maximize your production, even in the unconventional world. And this is just a breakout where we can take those key neurons that show that highly resistive zone, and she could go in with the client, show them where they missed it entirely, where they porpoised in and out, and can show by virtue of production how well this correlates it. Plus found a whole nother area that they hadn't even drilled yet that had the sweet spot in it. Now, one of the last things I want to cover is, as I'm drilling wells, a lot of times I try to have really good mud loggers, and I try to take the work that I'm doing and tying it to the mud log as I'm drilling the wells. So here's a case. This is actually from southeast New Mexico in the Delaware Basin, where we're going for a zone that's deeper than this, where you can see the point where we're drilling. But I'm tying my my patterns that I'm seeing directly to information I'm getting from my mud logger. In this particular case, I've got 80 feet here of limestone and dolomite, the upper 40 feet of which is highly fossiliferous. That exactly ties to this light blue color pattern right here. And the minute you get out of that pattern is the minute you leave the fossils behind and go into a combination of dolomite and limestone. So something as simple as the density increase from the fossils can create a rock property that's slightly different and gives you a different pattern. So here I'm seeing the next two patterns down are the dolomite and limestone. Now, a lot of times people will say, well, if you're looking at something like that and you have all these different patterns going on, how can you tell, what you're looking at? Well, Mother Nature is not always simple. In this case, I was looking for a chert, and that chert is right here in the mud log. And I could tie beautifully to the chert, but if you look at the complicated nature of Mother Nature here, you've got limestones, you've got chert, you've got chalk, you've got 2 or 3 different kinds of clays and shales, you've got clastics, and then you go back into limestones again. So as you're drilling these things all over the world, Mother Nature is not always simple either. And the patterns can give you a clue as to how your rock properties or rock types are changing as you're going. So in summary, I'd like to say that using multiple attributes and working on sample statistics can work in any depositional environment. It's not one and done because it is an iterative process to calibrate to your well data. And someone still has to interpret the patterns when they get them out in terms of lithology and stratigraphy. A good understanding of geological forms or the understanding of geologic processes in the subsurface is important. And it's also important to understand your attributes and what they can discern in the seismic data. But with this SOM classification process, you can find hydrocarbons that people can't see in the regular data.